So hi everyone, I'm Julie Farley and I will be your Virginia Tech Science Festival host today. We have Mrs. Davis class from Bell Heath. We are sixth graders. And also we have Emma Sparks, Ranit, and Vamsi here to present, and they'll tell you more about their presentation. So I'll turn it over to you guys.
Hello, everyone. First of all, thank you very much for joining, and thank you, Phyllis, for giving us this wonderful opportunity. Thank you, Julie, for coordinating with the school. And I just wanted to add that there is also Ahmed in the lab who would be helping run it with the experiments. So I think you can see him there. Yeah, okay. So the overarching goal of our presentation or our session today is to show physics with everyday objects, as in the objects that you see in your kitchen. There are different demonstrations that we'll be doing, and the way this will go is first Emma would start showing you some demonstrations with different types of liquids, and then we'll show some other demonstrations with Ranit and Ahmad there in the lab with some strings and plate.
Our first presentation is going to be about non-Newtonian fluids, which are basically just a mix between a solid, like this ball, and if you know about solids, you know when you put them into a container, they hold their shape, and a liquid, which will take the shape of its container. So if you combine them, and you can just do this in your kitchen with cornstarch and water, you make this really fun material called oobleck, and if you can kind of see it, it looks just like a liquid. But we're going to go do an experiment to show what will happen if you were to try and dive into a pool of this. So we're going to use this bowl of oobleck and this bowl of water and this hammer, which is going to represent our diver. So you can probably guess what's going to happen if I try and hit this bowl of water. It's going to make a big splash. But then when I try and do the same thing with the oobleck, it doesn't, because when you expose the oobleck to force, it behaves as a solid instead of a liquid. That's the difference between a Newtonian fluid, like water, it behaves the same in all circumstances, and a non-Newtonian fluid, like oobleck, which will behave differently if a force is applied to it. You can also see this if I try and pick it up and play with it a little bit. You can roll it in your hands. Oh, it's not happening. You can roll it in your hands and make it into a ball. A little bit of a ball. And then when you let it go, it looks just like a liquid again. So that's oobleck.
So what Emma showed, so you can experience that with other liquids also. The other kinds of non-Newtonian fluids like oobleck are toothpaste, ketchup, honey. Some kinds of honey, not all honey. So what happens is that when you hold a bottle of ketchup, it doesn't flow easily. So that's why you have to shake or tap at the bottom of the liquid bottle to make it flow. It's a liquid, but it doesn't flow like water. So that makes it a different liquid than water, which is what Emma called the non-Newtonian fluids. So there are different types of non-Newtonian fluids, one which moves when you force them to move, like toothpaste or ketchup, and one which stops moving when you put force on them, like oobleck. So oobleck actually behaves as a solid when you put force on them. So that's like different kinds of liquid, and which we work with in our lab, and you can also make in your home and see the fun.
How long did it take to make that?
How long does it take to make oobleck?
It's a little annoying because when you try and stir it, it behaves as a solid. But you just stick your hands into it and work it together. It's just cornstarch and water, so you just combine them in a bowl in your kitchen, and it can be done in 10-15 minutes.
So in the next theme, I wanted to introduce a few terms that will be really helpful to understand the physics of what's happening. The first term that I want to talk about is frequency. I know you might have heard it in different contexts, but I just want to say that frequency here, when we say, it means something that is moving rapidly. So this is what we are going to be using. So this string is taut on both ends. So you can see it is on either ends, and there is a shaker here on the right side, if you can see. And this shaker actually moves up and down, and that is what is going to give it some mechanical motion. So when we say frequency, referring to how fast this particular structure is moving up and down. Now, there are two things. When I say fast, you can think about the amplitude, you can think about number of times in a second. So when I say fast, or when I say increasing the frequency, I'm referring to number of times it is moving up and down in a second, not how much it is moving up and down. That is referred as amplitude. So the difference between them is amplitude is how far away it is going, and frequency is how many times it is vibrating in a second. So this is the system that is going to communicate to the shaker to move. So if you can notice here, it shows frequency of 80.3 Hertz. So Hertz essentially is what I just explained. So 80.3 means in 1 second, something is moving there at 80.3 times. So here frequency, you saw it, this is called signal generator. This is going to send electrical voltage.
So this,
Fire. Ahmed, were you saying something?
no. So I'm saying that through this wire.
Yeah, oh, yes. So the wire is called a BNC cable, if you are curious. And they were used in internet communication, but very old generation. Now there are faster products now. But anyways, so that's called BNC cable. This is a signal generator. We are sending the electrical voltage from signal generator inside what is called as amplifier, which is going to increase the amplitude. Remember, amplitude is not frequency. It is how far away the structure is moving, or how much higher it's moving. It's not how fast it is moving. That is frequency. It's not going to alter the frequency. It is only going to increase the amplitude. Ranit, you can go ahead and now show what happens as you change frequency and excitation. It's probably obvious now that the shaker is not moving and the string is vibrating. And I think Ahmed is trying to manipulate the frequency now. Very interesting if you can tell at what frequency Ahmed is operating right now, or maybe Ahmed can do that.
So now this shaker starts moving, and now you will see different shapes on the strings. So as you can see, the strings are actually attached at both of these ends. So there is no movement on this. So there is zero displacement on these both ends. These are called nodes. And the displacement is highest right about here, where you see that it's moving like up and down over here. So this is the highest amplitude. This is the antinode. And so this is also the first mode of natural frequency. So this is what you actually don't see, but this is what happens when you pick on a guitar string or a violin string. So any instrument which uses some kind of strings actually performs in the same logic, that you fix the length of the string, and then you can change the frequency and make different noise. Next time you hear some guitar or violin, think about this, and it's not magic or anything. It's just physics. By movement of the string, it emits sound.
So right now what Ranit is going to, or Ahmed is going to do now, is change the frequency of excitation. So again, the same scenario, he's going to change the frequency of excitation in the signal generator, and we are going to see what will happen on the plate. And at some points I will unmute it, and you can see that the sound made by the plate. The reason why you couldn't hear with the string is because that is a rubber band. It is not designed to make sound, and it is very thin, but the plate is too big. So you can hear, it can radiate more power, or it can move things around much faster, much better. That's why you can hear it. Give me a thumbs up if you can hear the sound and see the couscous beats moving and the pattern that it is forming. Perfect, thank you. And let's see what happens as Ahmed increases the frequency. You see the shape becoming a different shape, essentially those beats moving on to a different places. So what is happening here is, at some point, Ranit mentioned that there are something called nodes and antinodes, or there are places with less displacements and more deformations. So these beats are going and settling down at locations where the deformation is very, very small. I think something that I want you to notice is that at 300 Hertz, you felt a different sound. At this particular frequency, or what I'm trying to say is, not only the shape changed, but also the sound that you heard changed too. So I think the takeaway point that we want to make from these two demonstrations is everything that moves makes sound, and sometimes you can hear it, sometimes you cannot. For example, for the string, you could not hear it because it was very thin and the material was not something that was designed to make a lot of sound. And again, with the case of plate, you could hear it because it was a much wider structure and it could move the air up and down much more efficiently. And as you increase the frequency, the type of sound heard changes, and also the shape that the plate took and the string took also changes.
Thank you all for being here. All right.
Thank you for the
Thank
opportunity.
you all.
Thank you guys. That was awesome.
Thank
Yep, thank you.
you.